Hello everyone. I would like to thank IABM to provide us with an opportunity to speak today about object detection, opportunities, and limitations for media applications. Before we get into the subject, let me quickly give a background about our company and myself. Intera Systems provides software-based classification, quality control, and monitoring systems for media content. Our patent software is used by media companies for the QC of media content for a variety of technical parameters as well as audiovisual perceptual artifacts. It supports a comprehensive suite of checks covering standards compliance, regulatory checks, etc. Over the last 18 years at Intera, I have been involved in the development of multiple Intera products, including Vega Media Analyzers, Dayton Automated Media QC System. Currently, I am involved with the development of Vino, a content classification and moderation tool based on deep learning and advanced computer vision techniques. As technology improved over the years, so did the expectations from automated QC systems. The next generation of QC checks involved in-depth semantic understanding of content by identifying and extracting objects, events, actions, scenes, and spoken or visual words from the content and using them for specific purposes like content moderation, classification, indexing, and retrieval, etc. In our product, in our product Vino, we address the needs of automatic content moderation in media quality control. This covers use of stronger foul language, violent or disturbing content, nudity, sexual situations, health advisories like drinking of alcohol or smoking, drugs, religious or cultural concerns, and other regulatory requirements. There is some form of parental guidelines for TV and movie content in all countries, which are based on the level of explicit content, graphic violence, and profanity in content. Traditionally, human moderators are responsible for reviewing and rating or censoring content for the different audiences. Machine learning is now able to assist us in reviewing content much faster. We believe that our machine learning based systems can extract enough semantic information from content so that appropriate rating can be inferred from it. Object detection is a key ML technology for content moderation applications. Other technologies include action recognition, speech to text, visual text, natural language processing, etc. The focus of today's talk is object detection. Object detection involves detecting instances of objects from one or several categories, like people, faces, vehicles, firearms, or body parts, in an image. Typically, only a small number of relevant objects are present in an image, and their occurrence is rare in content moderation applications. Yet, the number of possible locations and scales at which they can occur is huge, making the problem quite challenging. Early computer vision methods were based on key points in an image and features like shift or fog extracted from these key points. Algorithms for generating region proposals like selective search, edge box, and multibox were developed, and features were extracted for these regions. Then SVM-like classifiers were built individually for each category. These methods were limited in application. They worked under controlled conditions with limited variability and didn't scale well for real life images in the wild. The breakthrough in object detection started happening from 2012 when AlexNet was introduced by Krzyzewski et al. It was a network trained on 1.2 million real-world images from the ImageNet dataset for the purpose of classifying them into 1,000 different categories. With 5 convolutional layers and 60 million parameters, it was able to achieve a top 5 error rate of just 17%. It combined a number of ideas like convolutional nets, ReLU activations, dropout layers, multiple GPU training, normalization layers, overlap pooling, smart data augmentation tricks that were already available and achieved a great milestone. Gershik introduced Region CNN in 2014 by adapting AlexNet for object detection tasks. Faster RCNN was introduced by his team in 2015. It is a highly successful deep neural network for object detection tasks. It consists of a region proposal network which proposes possible regions in an image which might contain an object, and an object classification network which checks whether these proposed regions contain an object among the list of supported categories or not. If yes, the network returns the bounding box of the region containing the object and the name of the object. This network was able to achieve 76% mean average precision on Pascal Visual Object Challenge 2012 test set. The key to using these deep learning based networks is transfer learning. It is a machine learning method where a model developed for one task is reused as the starting point for a model on a second task. We take the pre-trained faster RCNN model and change its classification layer to the categories of our interest. We then retrain the network with our own in-house data set. The process of adapting models for our specific needs is much more efficient than training a model from scratch, which would require huge data set of images and take weeks of training time. Faster RCNN is a state-of-the-art object detection network with excellent detection performance. It performs quite well on detecting small objects too. However, it is far from perfect. In the following, we discuss various challenges faced in object detection. Objects can vary in scale. Here, each candle is very small inside the image while the spider web is occupying the whole image. The number of instances of the same object can vary a lot from just 1 to hundreds. In some clean images, there is no background clutter, while in others, an object is surrounded by hundreds of objects. The shape of an object can morph in various ways. The amount of texture on the surface of an object has huge variations. While some objects like red wine may have distinctive color, other objects like mug may come in any possible color. While the shape of a bell is quite rigid and standard, a jigsaw puzzle may come in all possible shapes. An object detector tries to learn various patterns in images. However, it doesn't have any reasoning or judgment capability like humans. We have extensive background knowledge about real-world situations and object configurations, and we can easily reason about objects even if they are occluded. For example, in this image, as human beings, we can easily discern that a young boy is not having an alcoholic drink, even though the details of the can are not very clear. This is difficult for a machine-based detector. Interpretability. Deep learning-based networks are essentially opaque and hard to interpret. It's difficult to figure out what exactly they learn and how do they learn what they learn. Initial layers of the backbone convolutional network seem to capture low-level features like oriented edges and opponent colors. Indirect studies indicate that the final convolutional layers seem to learn higher-level concepts like faces, colored blobs, text, and geometric structures. The fully connected layers in the object classifier compose these rich features for final classification. However, how networks learn these abstractions is ill understood. When a network generates a false positive, it may seem ridiculous. This figure shows example regions which activate specific units in the last layer of an RCNN network. Row 1 unit seems to fire on human faces. The row 2 unit seems to fire on dog faces and dot arrays. However, in one odd case, it fires on the US flag too. Row 5 unit seems to pick up triangular geometrical patterns. Normally it is picking up houses, but it is also picking trains. When we as humans mistake something, we tend to confuse between similar looking things, but networks can make funny predictions. It is difficult to convince customers and investors about using technologies which are difficult to interpret. Networks like faster RCNN are supervised networks. Their performance depends on the quality of data set used to train them. However, preparing datasets for object detection is a time-consuming process. First, one must collect a wide variety of relevant example images from various sources. Then one needs to go through each image, identify bounding boxes, and save the ground truth in the database. If a new object category is introduced, previous images need to be re-annotated, thus increasing annotation activity with increasing categories. Variability is a big concern in datasets. Objects may not have been captured from various viewpoints or illumination conditions. Deep nets are particularly biased against rare events as there are not enough examples in the dataset. For example, datasets used to train autonomous vehicles almost never contain babies sitting in the road. In adversarial attacks, one can add a small amount of error to an image, leading to a completely different prediction by the network. In this example, a panda image has been slightly perturbed. Humans still see a panda, while the network now thinks that it is a gibbon. Such methods pose security and AI safety challenges, as it's not too hard to fool a network. Traditional ML techniques to make models more robust tend to fail against adversarial attacks. So far, only two methods have provided significant defense: adversarial training and defensive distillation. Humans have great ability in spotting objects in previously unseen contexts. For example, we would not have any difficulty in spotting a motorbike, a monkey, or a guitar in the examples here. However, such occlusions can cause deep networks to fail easily. In the left, a motorbike turns a monkey into a human. In the middle pic, the jungle turns the bicycle handle into a bird. In the last pic, the guitar turns a monkey into a human, and the jungle turns the guitar into a bird. Let me now move on to our own experience of developing object detectors for content moderation applications. We started with the baseline of faster RCNN network. We identified a set of relevant categories for violence, health, and nudity applications. We slowly built the initial data set of annotated images for these categories and trained our network using transfer learning techniques. However, initial results were below expectations. We started digging deeper. We identified areas where the network was getting confused with innocuous objects. We refined our dataset and added many negative examples. We modified the detector to support these negative categories. Some of the large categories were split into subcategories, and the dataset was updated accordingly. For example, the guns were classified further into small, medium, large guns, and tanks. In some cases, context was critical. For example, we introduced a category called armed uniform personnel. Presence of a uniformed soldier or policeman increases the likelihood of guns being present. Since we primarily work on videos, we added object tracking across frames to validate our detection also. Our system has a separate module for visual text extraction. We were able to use cues from visual text to further confirm presence of specific objects. So these efforts, we achieved significant improvements in accuracy. We train our network with high recall objectives at the expense of some loss in precision. Our system design is multimodal, where cues from audio, video, on-screen text, and captions are combined to make final detections. For example, visual text has been a great tool in reducing both false negatives and false positives for our detector. Let's look at some examples. Although we don't have direct support for identifying marijuana plants, we can see marijuana text on screen, and we are able to classify it under the drugs category. Here, we detect gambling by detecting specific artifacts like cards or roulettes. Here also, we can detect casino hoardings or website names, and from there we can infer gambling. Our network used to confuse this bottle as an alcohol bottle. Visual text indicated it to be an olive oil bottle, and this false positive was suppressed. Let's look at a few more difficult examples. These are some examples where our detector can now handle easily. Because of the angle or illumination, the shape of guns is not clear in these examples. By feeding our network with enough hard samples, we were able to train the network to learn the context around the guns and use it to correctly identify them. We believe that an ML accelerated human in the loop framework is the right approach with current level of technology. Let's quickly look at the strengths and weaknesses of human versus machine moderation. Humans struggle to memorize huge quantities of information like adult products, hair symbols, alcohol brands, faces for celebrities, cuss words, and religious symbols. Humans can also miss a few cases during long review sessions. Machines produce consistent and repeatable results, and if trained properly, they will not miss out objects from large vocabularies they have been trained on. Human vision may struggle in low illumination, background clutter, or for very small objects in a complex scene. Well-trained ML systems can easily outperform humans in these challenging environments. Our train detector can easily recognize the alcohol glass in the hand of the first image, the gun in the dark second image, wine bottles on the side rack in the third image, and an alcohol bottle camouflaged with the shirt color in the fourth image. There are many situations which are best handled by humans only. Current generation ML techniques lack general intelligence, and humans are needed to handle subjectivity and previously unseen context. In this example, a machine can behave strangely on unseen data. Here, our detector thinks that an alcohol bottle is present inside the letter O. Humans can easily reject this false positive based on the context around it. Here, our detector has classified a lining in the roof as a gun. Humans can easily spot this mistake. A detector trained on mostly Western nude content may not be able to classify Japanese nude content, exposing racial bias inherent in the dataset used to train the network. Humans have great ability for domain adaptation. Machines do not understand the societal context. What's okay in one region might not be okay in another region. These are two real life examples where left side of the image was allowed in the Western world, but not in the Middle Eastern countries. Human moderators are critical to address this level of subjectivity. In this table, we attempt to contrast human and machine capabilities on different parameters. Humans are expensive, machine moderation is cheaper up to 10 times. Hiring or training qualified human operators is expensive and difficult to scale. Machine implementations can be easily scaled up or down on the cloud infrastructure today. Humans have ethics, judgment, conscience, and reasoning abilities which go far beyond the level of current generation of ML technologies. Humans can easily extrapolate their knowledge into previously unseen data or context. Content moderation is a traumatic job for humans. Watching violent content for hours can have adverse psychological impact. Algorithms experience no trauma. If we look at the overall accuracy of detections, humans and machines are competitive, both having edges in different aspects. Machine detections are usually deterministic and produce consistent and repeatable results. Human consistency is generally good, but may fail at times due to lack of attention or stress. At Intera, we believe that ML technology should support and complement human moderators rather than replace humans. Our product window is designed in a way to extract huge amount of information from the video clip, which make the decision-making process for the human moderator quite efficient. A 1 hour movie could be reviewed within say 5 minutes. In Vino, the moderation is a two-step process. First, our ML model detect potential issues in a video clip. Then a human can quickly review them to make final decisions. Regular samples from video are also extracted for quick review so that humans can notice a missed detection. Before we close the session, let's look at some of the research directions in which object detection technology is evolving. Research in object detection is alive and thriving. Here we mention few directions which are quite promising. Few-shot learning is a set of principles for adapting a network to learn about a new category based on only a few examples. One-shot learning is where network could be trained to identify a new category using just one example. Humans are quite capable of one-shot learning. So far, robust few-shot learning algorithms are still in research. Domain adaptation is the ability to apply an algorithm trained in one or more source domains to a different but related target domain. The idea is to minimize the amount of training required in the new domain. An example is to adapt a network trained to recognize large American cars to start recognizing small Indian vehicles. Incremental learning is a method in which input data is continuously used to extend an existing model's knowledge to further train the model. This can help in reducing false positives and negatives over time in a deployment. Compositionality assumes that structures are composed hierarchically from more elementary substructures following a set of grammatical rules. Thus, substructures and grammars can be learned from a finite amount of data, but will generalize to combinatorial situations. Such methods offer the ability to extrapolate beyond data that they have seen and to be able to reason about the system. We hope that we have been able to provide a good overview of the challenges and opportunities in the object detection for media applications. We welcome you to visit our website interasystems.com to know more about content classification and moderation solutions. Thank you.